Hello and welcome to the first lecture of radiation heat transfer. So I will firstly give the number of lecture 1. Okay. So what do we mean by radiation? Now the the fundamentals of radiation can be described by two theories. One is electromagnetic wave theory, another is the theory of quantum mechanics. Like, I hope that you have already heard that light that can be perceived as either wave or particle. So that is known as the, I mean, wave particle duality, right? So like this, so light is basically a radiation. Okay, I mean that is the visible part of the radiation. Okay, so here we will deal with the only the part that comes under the mechanical engineering. Okay, I mean what I am meaning by that is we have a black box like this. Okay, now this black box is either your EM wave theory, okay, or your quantum mechanics. Okay, so here in this black box we are giving some input like this, and that is the raw input, and here we are getting the theory of radiation. Okay, so as mechanical engineers we are interested with these things. Okay, like I can say you that proof this E equal to h nu equal to hc by lambda. So this was derived or shown by Max Planck. Okay, but we don't have that much interest. Okay, that from where it is coming. We know that from the point of view of quantum mechanics, this is true. Okay, that is energy can be conceived as discrete point energies. Okay, so first of all we need to understand that is the difference between radiation, conduction and convection. Now here let me honestly confess you that is uh, when I am still a student, so throughout my whole life up till now I was very confused with radiation. What is this? Because I can feel conduction, I can feel convection. Now, conduction, you see that we, I can say you that okay, in the micro level, molecules are vibrating, and through that vibration, the energy is being transferred. Convection is molecules are moving, carrying the heat along with them. But what the hell is radiation? Because radiation does not need any molecule. That is the basic difference. So then how the hell the heat is getting transferred? Then someone will answer you, okay, there are some electromagnetic waves which are propagating. Then you can say, okay, I have heard about the wave in sea, I have heard about the wave maybe in any other thing, any wave in air or like that, but those waves are also having some molecules. So to get a physical insight, now I can say you that okay, forget about wave, can you think about photons? Photons are discrete particles having discrete energies. Okay, now it's a bit understandable. That is a matter which is above 0 Kelvin, okay, or if it is having a non-zero absolute temperature, then it will emit photon. Now it is physically perceptible, right? So the first point is it can be uh, the phenomena of radiation can be described by either uh, EM wave theory, okay, or your quantum mechanics, okay. And how? Because we are saying that we can perceive them as photons carrying energies, okay. So this is the basic of radiation, that it does not need any medium. Now this thing we know from our very early school days, from maybe class 8 or 9, okay. So I was in Bengali medium, and I can still remember that we were asked to write the differences between radiation, convection and conduction, okay. So the first difference we used to write is the definition, and the second difference we used to write that convection needs a medium, conduction needs a medium, but radiation does not need any medium, okay. But then we also thought that how the hell then the heat is being transferred, okay. And still I cannot feel it, okay. That is how the heat is being transferred, okay. I can see light, and I can also feel some uh, physical phenomena, okay, that is heating by fire. So, and also if you do an experiment that in vacuum, if you put a very high temperature source, and if you put at the other surface a very low temperature surface, then you can see a heat flux from that surface. I mean, not see, you can feel. So that is because of radiation. So as there is vacuum, we cannot say that there is conduction happening or convection happening. So there must be a mode of heat transfer, and that is named as radiation. So these are the two basic pillars that we know before starting radiation. That is, it can be described by electromagnetic wave theory or by quantum mechanics, because it can be either perceived as waves or photons, and it does not need any medium. But then the question comes that if the medium comes in between, then what happens? Is still the radiation is there, the same radiation which was there without the medium, if it is still there or not, or or the radiation is being modified, or the radiation is not there because of the presence of the medium. So that those things we will cover, okay. So continuing, let us explore the differences between conduction, okay, and convection and our dear radiation, okay. So I will choose a different color. Let me see that if I have white color or not, okay, this color will be fine. Now conduction needs a medium, okay. What the hell, this is black color, uh, okay. Now conduction needs a medium, so medium right, here also medium right, but here medium is not necessary. I am putting a cross, but the thing is it is not necessary. It does not mean that if there is a medium there will be no radiation, okay. Medium can be there, or it is it can be a medium free zone or a vacuum, okay. Now this was the first difference. Second difference is that the conduction and convection deals with differential equation, okay. Differential, but radiation will deal with integral equation. And what is the reason? The reason is that the length scale, or I can say the minimum length scale, or I should say that characteristic length scale, or characteristic length scale is very small. Okay, so I mean, what is the minimum characteristic length scale in conduction? It is the mean free path. Okay, mean free path in solids actually, because when we say conduction, then we generally mean solid, but conduction can happen in fluid also. Actually, conduction is there. There is nothing called a separate thing like convection. Convection is conduction plus advection. Okay, and here the characteristic length scale, or I should actually write the minimum characteristic length scale, is also very small. Is also very small. So these are the mean free paths in a fluid, or okay, mean free path in fluids. But here characteristic length scales can be very large, in the order of 10 to the power 10 meter maybe. Okay, these are the reason that we have to deal with the integral equation, because if you have to deal with the differential equation, then you have to think about energy balance for an infinitesimal control volume, which is generally not possible for radiation. Okay, and what else do we have? Okay, here unsteady problem can be there. Unsteady problem can be there. Okay, okay, so this is the fourth point I have right. Four. Here also unsteady problem can be there. Okay, but here problems are generally steady problem. Why? Because you see, you just think about light. So light is also a radiation. Now the speed of light, can you think about anything or any instrument that can compete with speed of light? Not, right? So radiation is supposed to occur almost instantaneously. That is why we think that we don't need to consider the time variation of temperature. Okay, I mean, obviously if there is a chamber having a very high temperature and you put a surface inside it having a very low temperature, then you can ask me that what will be the uh, temperature variation with respect to time. That is a pertinent question. But if you ask me that how much time it takes, okay, for the radiation heat flux to go from here to there, okay, that is almost negligible. So radiation heat transfer occurs almost simultaneously. Okay, I mean not simultaneously, instantaneously. Clear? So, and finally, if radiation is a surface phenomena or a volume phenomena. Surface phenomenon, because it is a single thing, or volume phenomenon. Okay. So surface phenomenon or volume phenomenon. So if you consider a solid, okay, so here I will draw a solid. So this is a solid. it is having its molecule very closely packed, very much closely packed. So even if the molecules are at very high temperature, then you can argue, okay, because the molecules are at very high temperature, and you just said that if anything is about 0 Kelvin, if anything is above 0 Kelvin, then it will emit radiation. Sorry about that. Just sorry about that. I had to write a very urgent email. So let us back to where I stopped. I was talking that about that the radiation is a surface phenomenon or a volume phenomenon. So for solid, even if the molecules are having a very high temperature, then the molecules should emit radiation, because I have already said that if anything is having temperature higher than 0 Kelvin, then it will emit radiation. So this molecule will emit radiation, it will, so that radiation will get absorbed by this molecule, or it will get reflected by this molecule. So like that, these emissions cannot go out, or a very minimal amount of radiation can go out from this solid. So anything that will come from this solid as radiation heat transfer will come from the surface. On the other hand, if I consider gas, okay, maybe gas or any fluid, so here the molecules are having enough space between them, and that is why radiation can come out from this volumetric zone also. Or I can say that if something is going in, then it can penetrate through also. So obviously the radiation intensity will change, and what is radiation intensity, that I will define separately. Okay. So for gas and liquids, we can say that, not for actually liquids also, but mostly for gases, we can say that radiation is a volumetric phenomena, and for solids it is a surface phenomena. Okay. So I have already told you that this series will be uh, not in that depth or detail, because I have some separate objective in my mind. But still, if you are starting radiation from basics, I hope you are getting the concepts. Okay. But just as is the condition for any series that I have done, you should write your doubts or suggests or anything that you are facing in the comment box. Okay, that I will take care of. Fine. So this was the basic of radiation. Okay. Now radiation is really scaring. I mean, it has scared me. Okay. Because every time I was like कि यार कंडक्शन समझ में आता है, कन्वेक्शन समझ में आता है, लेकिन व्हाट द हेल इज रेडिएशन. Okay, because anything, if you don't take it from the fundamental zone, na, it will not be embedded into your blood, and that is why radiation was still, uh, until and unless I get the grasp on the quantum mechanics or EMF theory, I am sure that I will not be in the position to say that, oh, that okay, now I know that what is radiation. Okay, but still I am trying to teach you, okay, all the things that I know. Now let us go for the EMF spectrum. So what the hell is this EM wave spectrum or electromagnetic spectrum, not EM wave spectrum? Okay, so the thing is, as I have said, that the radiation is nothing but some waves. So a wave is having a particular wavelength, right? So we say that this lambda is wavelength. Okay, let c be the wave speed or velocity. Okay, then we know that c is equal to n into lambda, where this n, or I should write nu. Okay, nu into lambda, where this nu is the frequency. Okay, and our dear Max Planck has said E is equal to h nu. That means E is equal to hc by lambda. Okay, so any wave will have its own speed, its uh, its speed, its wavelength and frequency, and these three are correlated, right? So if you give me any two, I can find the third one. Nice. Up till now it is, I think, okay. Now let us say that I have a partition here, and on this side I have medium 1, and on this side I have medium 2. A wave was traveling like this. It was traveling like, okay, everything is fine. I am traveling in medium 1, but suddenly it has to pass into medium 2. Okay, so the same wave, this is a wave, it was traveling in medium 1. So you were just in your fourth year or third year, and you are like that, okay, still 1 year is left, I can enjoy, I think. But when your college ends, then you feel like, yeah, in my college days it was a bit okayish. I mean, I did not have this much politics, and now I am in this company, everything is different. So how can I cooperate? You have to change your speed, you have to change your wavelength, but something you can keep as your constant, that is your morality, right? So your situation might get changed, and according to that you have to adapt yourself, and you have to change something, but something you have to also keep as constant. So for this wave also it will be the same thing. Whenever it is going from medium 1 to medium 2, which thing can remain constant? Pause the video and think independently, think by logic, that which thing can remain constant. The answer is energy, because energy can neither be created and cannot be destroyed. So energy will be constant, or in other words, energy in medium 1 is equal to energy in medium 2, or I can say h nu in medium 1, or I would write it as nu 1. Okay, and h is a constant, that is will be h nu 2. That means your frequency should remain constant. This is a very important conclusion. So frequency will not change with medium, but now c, so frequency is what? C by lambda. That means my c, okay, so from this formula I can write that my c1 by lambda 1 is equal to c2 by lambda 2. Okay, now what happens is that in a medium, with refractive index n, okay, speed of a wave is equal to what? C naught by n, where C naught is the speed of that wave in vacuum. Clear? In vacuum. So this you have already studied in your class 10 or 10 plus 2 physics also, that is the definition of refractive index n is equal to what? C naught by C. Clear? So here it will be actually, so if it is having, okay, so medium 1 is having a refractive index of maybe N1 and medium 2 is having a refractive index of N2. That means I can say that my C naught by N1 by lambda 1 is equal to C naught by N2 C naught by M2 by lambda 2. That means I can say that lambda 1 N1 is equal to lambda 2 N2. Okay. So that means wavelengths of the same wave in two different mediums are correlated by this relation, and speeds of the same wave in two different mediums are correlated by this relation. Clear? So this was also very important, because if you change the medium, then the uh, wave speed as well as the wavelength will change, but the frequency will remain same. Clear? Okay. So now we understand that there are infinite number of waves having various wavelengths. I mean, there can be infinite number of wavelengths. Okay. So based on the wavelengths, we define something called electromagnetic spectrum. So that is nothing but we define a axis in which we plot wavelength lambda, okay, and we segregate the span of wavelength, okay, ideally from minus infinity. So this I write as 10 to the power minus 4, this I write as 10 to the power minus 2, this I write as 10 to the power minus 1. Now I will not tell you any lie, I am just copying it from a copy, okay. I don't remember it exactly, because I find that not all the things I should remember. My brain is not a storeroom, it is made for creation. So dot 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 infinity, and here dot 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 minus infinity. Clear? So now uh, I will, what I will do is I will draw some lines, dotted lines, okay. So these are the segregations, okay. So from this onwards, there is some point, from this point onwards the rays are called gamma rays. You also don't need to memorize all these things like a donkey, okay. Memorizing is a great skill, but use it in some relevant places. You have to memorize your girlfriend's birthday, otherwise it will be a catastrophic, right? Okay, this is X-ray, and now this is ultraviolet rays or UV rays. Clear? And this is the zone where we are interested in, because that is why I should show it with some different color, brightest color. This is the thermal radiation, okay, thermal radiation. And this is also a very celebrated zone, this part. Why? Because this part is your visible radiation, okay, visible part I would write, and this is your VIBGR, the 7 colors which we can see, the 7 fundamental colors. And then again we will have from this to this infrared. Okay, so there are some gadgets which can capture infrared. Okay, and that is how they can see in night also, like cats. Okay, and uh, infrared. Okay, and from this onwards we will have microwaves. Clear? So this is our EM wave spectrum. So very high-fi name, spectrum. Okay, but nobody says that. I mean, why spectrum? Why cannot I name it as EM Soham? Okay, why cannot I name it as EM dog? Okay, so there is nothing in those fancy names. You have to just understand. Okay, that is we are just segregating the wavelength thing, the wavelength axis based on various wavelengths. We are segregating. Now you see that E is equal to E is equal to h nu, or it is equal to hc by lambda. Okay, so if lambda is very large, then my energy is very low. So if I hit you with a wave having a very high wavelength, then it will not harm you that much. That is why we can sustain the visible part of the radiation or the thermal part of the radiation. But whenever you get exposed to very high frequency wavelength or very low, very high frequency waves or very low wavelength waves, then you are exposed to very high amount of energy that can harm you seriously. So when you undergo X-ray, okay, when you undergo X-ray, so if you have broken your leg or hand during playing football or during any other thing that you might do loving, okay, so uh, during those acts, if you have broken your any of the body parts, then you have to do some X-ray to verify it. Now if you are someone who likes to break his or her parts very frequently, then you have to do frequent X-rays, unless otherwise you are sure that okay, I have broken my hand, please don't do X-ray. I am sure that I am such a person, I will sure break my hand. So you don't have to do X-ray. The money will also be saved. And other than that, if you can really do that, that is, I don't need to do X-ray, I'm sure that here is the compound fracture, then not only your money will be saved, but your that body part will be saved from the harmful X-ray. If you often get exposed to rays like X-rays, gamma rays, even UV rays. So UV rays, we know that they are very harmful to us. So can you imagine that how harmful can X-ray to us? Okay, so that is why if the X-rays, sorry, if the wavelengths are very small, then you can go for it. Oh, sorry, you cannot go for it because it is having high amount of energy. Okay, so now we have studied the EM waves, I mean EM spectrum. Okay, so now there is something called solid angle. Okay, we need that, and why we need that I will tell you. But before that, let us uh, see that what is solid angle. So concept of solid angle. Okay, concept of solid angle. So what is an angle? We can say that angle is defined like this. I don't need to say some fancy definition. We all know that angle is this. And if we have an arc, and if we know the distance that this is r, and this arc length, okay, is S. So then theta is equal to S by R, that we know. Clear? Now this angle is a 2D concept, right? Angle is a 2D concept. Now, have you seen ever a watermelon like this? So it will be maybe like this. Okay. Let me see if I can draw a very nice watermelon, juicy, nice watermelon. Okay. So the bottom part should be green, right? Because it is watermelon. Okay. So have you ever seen a piece of watermelon like this? Okay. So it is a very tasty watermelon. Okay. Clear? Now this is the center of the watermelon. Okay. I mean actually the watermelon was like this. I have cut out this portion. Now can you see that I can see that this is some kind of, I mean this space here is some kind of, if I take an intuition, this is some kind of a 3D angle concept. So this is a 2D angle, this is a 2D angle, but inside this whole region this is a 3D angular concept. Okay. So if the area subtended by this surface is A and this length is, all over this length is S, okay, then the solid angle is defined as A by S square. Okay. So it is very much analogous to theta equal to S by R, and it is area by S square. Okay. So let us see that how can we define infinitesimal solid angle in spherical coordinate. Okay. So if I draw the spherical coordinate, this, okay, again this, okay, and honestly I don't need this part. Okay, now I have to draw the sphere. So I will only consider this much part of the sphere. Okay. So now I can draw a small element like this. I think the diagram is not very impressive. Okay. I need to draw it afresh. Okay. So I don't need that much big diagram, a smaller diagram would be enough. Okay. So what I need is this one. So this is the smaller chunk, okay. This is the smaller chunk. Let me name the chunk as A, B, C, D. So I hope that this part is clear as a part of a large sphere. I hope this part is clear or evident as a large, I mean as a part of a large sphere. Okay, now I have to use the colors very judiciously. Okay, so mhm, this one or maybe, okay, it's okay. Now here like this, and to draw these lines I will draw them by any other color, maybe with this one. Let me see. This is not good. I mean এই একটু একটু পরে কথা বলছি মা, হ্যাঁ একটু পরে কথা বলছি। So if I draw it like this, then I think it will it is not very impressive drawing, I guess. I need to draw it afresh. Okay, because drawings are the things that can embed you the concepts in your subconscious mind. So drawings need to be very much elaborative. Okay, first I should draw uh, that watermelon part. First I should draw that. Okay, mm. Mm. So this can be one arc, this can be other arc, and so this will be one, and not this one but this will be other one. Okay, now it is fine, and now one should be this. Okay, and the other should be at this position. Now I will draw this one with other color. Okay, so this is a small chunk, this is the small chunk. Okay, and this is the center of the coordinate axis. Let me draw the coordinate axis. So it's one axis, and actually this should meet here, so I will draw it like one is this, another is this. Okay, now it is fine, totally fine, right? So this is a part of a sphere. Okay, and this is one, and if I extend this a bit, okay, again I can do it like this. Okay, now it is fine, the drawing is good. So this total thing is a part of a sphere. If I show you like this is a sphere. Okay, I hope you can see, I mean uh, it is extending, and it is a part of a sphere, and I hope that is clear from the drawing. Okay, now this is called azimuthal angle, this angle. this angle is called, I will name it as d psi, okay, azimuthal angle, and this piece of area, so this is an infinitesimal area, this area is an infinitesimal area, and this is our dA, clear, and the radius of this sphere is r, this angle is theta, okay, and this angle and also this angle, these are same angles, these are d theta, this is also d theta, clear. So and there should also be another angle, okay, and what is that angle? This is psi, no, okay, r theta psi. So this is our cylindrical coordinate system, okay, so r theta psi, this coordinate system. So now if I ask you that this area, this infinitesimal area is subtending, okay, a solid angle at this point, okay, that is this, okay. So this solid angle that we will be found, okay, we will be found, sorry, this solid angle that we will be finding is nothing but the solid angle subtended by this area at point O, okay. So now let me name this area A, B, C, D, and it is having a magnitude of dA. So solid angle subtended at O by area ABCD is equal to d omega, that we know that dA by r square, because this total distance is nothing but r, okay, this distance is nothing but our r, clear. So now let us find the dA. So it is an infinitesimal element, so I can approximate this as a rectangle. So if I have to find the area of the rectangle, then this side into this side, okay. So what is this side? So AB, so I can write this as AB into BC by r square, okay. Now AB is what? Let us write separately. AB is what? This we know as r, right, and this is d theta, that means AB is r d theta, clear. So AB is r d theta, and BC is what? So BC is this much, BC is this much, okay. Now this is d psi. Can you see that this angle here, this angle and this angle, these are actually the same angle, okay, these are actually the same angle. So I can write that this BC is equal to, because this is r and this angle is d psi, this will be r d psi. So this will be r d psi, clear. So if it is now clear that AB and BC are this, so that means from this we can write our d omega is r square, let me see if I have done it correctly or not. No, I have not done it correctly. Okay, because why I have not done it correctly? Because see, if I consider this circle, so for for this circle, this is the center and this is the radius. But for this part, this is not the circle. I mean, for this part, this is not the radius. for this part the radius will be this one. Why? Because for this part the circle is actually like this. Okay, you can draw it separately. Okay, or if you can make a 3D model, that would be much better. But I hope I can make you understand that if I consider this part, then the circle is not like this, the circle is like this. Okay, I hope you are understanding, or if you are not understanding, maybe I can do a separate thing. Okay, let me try. So what I will do is, now this is a sphere. Okay, consider this as your sphere, and how can you cut a different part, I mean a part like this, or how have I cut a part like that? So can you take another circle like this? अरे यार क्या बन गया? Can you take another circle like this? So this is also a circle having the same center. If you see from this side, this is also a circle, this is not an ellipse. Okay, now can you take another circle like this? uh, Not this color, maybe with this color. It will be like this, and it will be another circle at an angle. Okay, at an angle with this. Let me not draw that side, but it will be another circle with, so all these are circles have at different angles. Okay, so this is also a part of a circle but at different angle. So now I will draw two more circles, one circle like this, clear, another circle like this. Which color should I do? White. Okay, so now if I remove, okay, if I draw only this part of the circles, okay, only this part of the circles, this and uh, where is the, okay, this and these parts are hidden. Okay, these are also circles, these parts are hidden. So can you see that this is the area, this is the small chunk of area, and where this is the center. So what I have drawn is this area. Okay, so for this part, what I was talking, that for this part, this is the circle, and not, I mean, and if this is the circle, then the radius is this, not this one, and if this is the circle, then the radius is this, not this one. Okay, that is why for this AD or BC, the radius is this and not this or this. Okay, so that means BC will be this radius. Okay, let me draw with the white color. So BC will be this radius. Okay, now this radius is what? You see that if this angle is theta, this angle is theta, okay, and this is r, so this angle is theta and this is r, so this part will be r cos theta and this part will be r sin theta. Now you can argue with me that this part and this part are not equal, but as this area is very small, that means this and this, that is this part, or I should say this part and this part, they are almost equal. So this is equal to r sin theta, equal to this. Okay, So BC is equal to r sin theta, okay, r sin theta d psi. So this will be r square, area will be r square sin theta d psi by r square, that will be, okay, sin theta d psi. Clear? So this is the definition of the infinitesimal solid angle, d psi equal to sin theta d psi. So again the symbol is not important. This is what? This is I mean which angle? This is called the zenith angle or the polar angle, and this is the azimuthal angle. So those things should be clear, that theta is this one and psi is this one, okay, this angle or this angle. Theta is this angle, psi is this angle, okay. So this was very important. Clear? Okay. Now if this is clear, then now let me talk that why do we need this concept of solid angle. So see that if you consider a particular point, from this point there can be infinite radiation rays, infinite radiation rays. But if you specify the solid angle, okay, so you say that this is my surface, but you have to specify that how many rays are striking this surface. That you can do by specifying the solid angle. If you specify the solid angle, then you are specifying this inside region, inside region, that is a 3D region. So in that 3D region, some finite number of radiation rays can be accommodated, and this has a term called pencil of rays, okay, pencil of rays, okay. That is why we need to specify the solid angle which is subtended by an area, okay, which is subtended by an area at a particular point. So radiation can go from that solid surface to that point, or radiation can come from that point to the solid surface. For both of the cases you need to mention the solid angle, okay. So this is the solid angle. Clear concept of solid angle, and we need this because there are so many radiation ray direction, infinite number of radiation ray direction, okay, that can be there, but you need to specify some finite number of radiation rays, otherwise it is meaningless, okay. So solid angle thing comes because radiation depends on the direction. Essentially you see solid angle is accommodating this theta and psi, and theta and psi means if you change this theta, I can show you like this. So this is the line at an angle theta. If you decrease theta, it will go like this. If you increase theta, it will go like this. That means if you play with theta, then you are playing with this direction. Similarly, if you play with psi, okay, so I can say that if this is my another coordinate axis, then this is my psi, I can say that, okay, this is my psi. So if this is your psi, then you can say that I can have a direction like this for psi, and I can rotate it like this. I think this color is again not visible, I am sorry for that, you will take this color on. So this is the direction at an angle of psi. If I decrease psi, then I will take this direction. If I increase psi, then I will be taking this direction. So essentially if you change the psi and theta, then you are changing the direction. So because radiation is direction dependent, that is why we need solid angle. Okay. Now if I was having that my radiation is only dependent on theta and not on psi, then only the concept of the 2D angle, the angle that we have already studied throughout our academic journey, that angle would be enough. If my radiation is dependent only one angle, either theta or psi, then it is enough to have the concept of a 2D angle. But when it is dependent on any direction in a 3D space, then it boils down to a 3D system, and that is why we need a 3D angle concept, that is the solid angle. Clear? So now we are at a comfortable zone to study the radiation intensity. Okay, the radiation intensity. So what is radiation intensity? See, as mechanical engineers, we are we are mostly concerned about the heat flux or the heat energy that is flowing, heat energy flowing. Okay. Now that means I have to define radiation or radiation heat flux in terms of watts. Okay, in convection we say that this is my heat flux, this much watt per meter square. In conduction also, or we say that the heat transfer rate is this much watt. So if Q, okay, Q is the heat energy flowing, okay, or I should write radiation heat energy to be more specific, radiation heat energy flowing through an area, through area dA, okay, and my I is what? Radiation intensity. Clear? Now I will define this. Okay. So radiation intensity is defined as is defined, or at a point, radiation intensity at a point is defined as radiation energy flowing per unit time, obviously. So I can just put a dot here, or I can put a dt here, per unit time, per unit solid angle, per unit wavelength. Okay, I think I am not missing anything. Okay, and obviously it is defined as per unit, not area but projected area. So it has the definition of the radiation intensity is, it is the energy flowing through a point per unit time, per unit solid angle d phi, per unit wavelength d lambda, per unit projected area. And what is this projected area? That is area normal to the ray. Okay. So what does that mean? That means that if this is a point, okay, now you can define any area, So this is an arbitrary area, and this area is having a normal like this. So this is n cap, and this area is having a magnitude of dA. But now my radiation here is coming, what? My radiation here is coming like this. Yeah. what has happened? Okay, okay, coming like this, solid angle. So this is the solid angle, clear? Or okay, so I will bring the concept of solid angle separately here. You consider only one ray of radiation, one ray of radiation coming like this, and this is coming at a direction having an unit vector small s cap. So what is the area? Okay, what is the area in this direction? That will be something like this. Okay, so in terms of dA, if I have to write this white area, so I will say this as A B C D, and this green area is A dash, B dash, C dash, D dash. Okay, so this white area A B C D is nothing but is a component of this green area. So this area into cos of theta, and theta is what? I hope that you have already got that. Theta is this angle. Okay, if I extend this like this one, theta is this angle. So I can write this cos theta as my S dot n, clear? So I can say that my DAP, dA projected is dA into S dot n, clear? So here instead of DAP I could have written dA cos theta, or I could have written dA into S dot n, clear? So this is the definition of the radiation intensity. So we need ultimately this Q. Please have this definition of radiation intensity crystal clear in your mind. Okay, so this is the this is the total radiation energy, total radiation energy Q. We are interested in this, but to deal with radiation, see, this radiation energy is the total radiation energy. We don't say that in this direction what is the total radiation energy that is flowing through this surface. We simply say that what is the amount of radiation energy flowing through this surface. So when we are saying Q, we don't bother that in which direction you are talking about, in which wavelength you are talking about. Okay, so we don't consider these things. So these things are independent. I mean, this is the total radiation energy flowing through a surface. Again, when in the interview someone is asking you that, can you tell me that what will be the amount of radiation energy flowing through that surface? So the moment he or she says that radiation energy flowing through that surface, that will not encompass anything like direction, like angle, like wavelength, frequency, anything. So those things are not in this Q. That is, but radiation itself is a direction dependent thing. So the thing is that if I ask you that what is the amount of total energy flowing in this surface, so this will be the summation of this ray, this radiation ray, this radiation ray, this radiation ray, this radiation ray. There can be infinite number of radiation rays throughout the directions, throughout the range of wavelengths, because each radiation ray can be considered as a wave. Those are having different wavelengths. Okay, so each radiation ray can have different direction, that is why they can have different energies and different wavelengths, that is why they can have different energies. Okay, so if you are talking about Q, then you have to sum over all this radiation rays, and this radiation rays is represented by this I, radiation intensity, which takes care of this solid angle, and that means the direction and this wavelength also. Okay, so that is why we have defined something called radiation intensity, otherwise we cannot deal with radiation. Clear? So this is the concept of radiation intensity. So let me see that if I can stop here or not. Okay, no, I will not stop here, I will extend it just a bit. Again, if I am having a surface like this, like the previous one, okay, so there can be two concepts of solid angle. Okay, one is, you can say that from this point, what is the amount of energy that is leaving or incoming. Okay, so see, if some energy is incoming at a point, so you are concerned about this point, some energy is coming, from this direction, then your question will be that what is the solid angle, that is encompassing all the radiation rays coming from this direction. Again, if some energy is going from this point, then again you can define a solid angle like this. Okay, then again your question will be, what are the number of ancillary rays that is going, or that is being included in this solid angle. Okay, so if you increase this solid angle, then the amount of energy incoming will increase. If you increase this solid angle, then the amount of ancillary rays outgoing will increase, that means amount of energy outgoing will increase. Now see, if now this is your area, okay, and energy is coming from this point, okay, so energy is coming from this point to this area, then you will be seeing that what is the solid angle subtended by this area to this point. Okay, what is the solid angle subtended by this area to this point, that will give you the information that what are the number of pencil rays which are coming from this point to this area, okay. So those pencil rays only will accumulate, or those pencil rays will only contribute this energy which is striking this area. Clear? Okay, so this was one very important concept, it was just a concept and not any other thing. So should I define something else? Okay, so just I will define that what is a black body, and I will then continue from the next lecture. Okay, so what is a black body? Okay, sorry, black body, this introduction will take a bit time, so maybe I will take up this from the next lecture. Okay, or I have time or not? No, I don't have time actually. Okay, so we will take up this lecture with the concept of black body from the next day, and until then, bye, take care and thank you.